Hello, and welcome to this lesson on latches. Latches are great little digital circuits because they enable us to have memory. And we'll see how that works. This lesson, we're going to look at 4 different types of latches. We're going to first look at the most basic version, which is the SCR Latch. Then we'll look at the S0 R0 latch, which is a little bit of a tweak of the SR latch. We'll use that SR latch, S0 R0 latch, and build up what's called an SCR latch. And finally, we're going to talk about the D Latch, which is the latch that we'll use moving forward. And as we'll see, each of these concepts sort of build on each other until we get with the D Latch, which is what we want. And that's what we'll use in the upcoming lessons. Now, before we can talk about the latches, we need to talk about 2 types of new logic gates that we haven't talked about yet. The first one is called the NAND gate, or the NOT AND gate. And we have the NOR gate, or the NOT OR gate. Looking at the NAND gate first, let's go ahead and draw its logic symbol. It takes 2 inputs, we'll call them A and B, and is just an AND gate symbol with a little inverter dot there on the end. And we'll say it as output F. So to draw the truth table for it, we have A and B and F. AB is 0, 0, 0, 1, 1, 0, 1, 1. And F, remember, is going to be the inverse of AND, so it's going to be 1, 1, 1, 0. So that's our truth table for the NAND gate, just the inverse of the AND truth table. Now, the NOR gate is going to look basically the same. We'll have inputs A and B. And here we draw it as just an OR gate with, you guessed it, just the inverter symbol there on the end. Let's call its output F. Let's draw the truth table for the NOR gate. We've got A, B, and F. Let's populate the input side, 0, 0, 0, 1, 1, 0, 1, 1. And this will be the inverse of the OR gate truth table. So we're going to have 1, 0, 0, 0. Now there are 2 observations that I want you to make about these truth tables. And those observations are, notice what input value dominates this output. And what I mean by that is over here on the NAND gate side, if any input is equal to 0, F is equal to 1. And on the NOR gate, it's sort of the opposite. Here we see if any input is equal to 1, then the output F is equal to 0. That's going to become important when we talk about our latches. So let's go ahead and do that. Let's talk about our first latch, the SR latch. So the SR latch is made up of 2 NOR gates drawn concurrently. So I have NOR gate 1, give myself a little more room, and NOR gate 2. It takes an input R, which stands for reset, and an input S, which stands for set. And they individually feed into their respective NOR gates. And then we have the output. This top one goes to what we'll call Q, and the bottom one goes to what we'll call Q naught. Now here's the fun part. We take the Q signal, we're actually going to route it back around to be the input of the NOR gate that's taking from set. And we'll do the same thing with the Q naught signal and wrap that around. So now let's take a look at how that behaves. Let's go ahead and draw out a truth table for this circuit. So we'll say SR is the inputs and Q naught as the outputs. And let's start by writing a 1, 0 on set and reset respectively. Now we've got a 1 on set and a 0 on reset. Now this is where that input domination concept comes into play. So remember, if we go up and look at our NOR gate, remember, if any input is equal to 1, it does not matter what the other one is, it's going to be equal to 0. So we are definitely going to have a 0 over on this side. This is what stops us from having this like infinite loop of things happening. So 0 comes around over here. Now 0, 0 in our NOR gate is equal to 1. So we have Q equals 1 and Q naught equals 0. When Q is 1 and Q naught is 0, we refer to that as our set state. Now, the cool part. What if we take these values, S and R, and we return them to 0? Let's take a look at what happens there. Let's see, we'll have 0 and 0. Now remember, 0 doesn't dominate, so it's only in the case where we have 0, 0 do we get an output 1. So these outputs are still hanging out here, and so we have a 1 here and a 0 there. So this R line has 0, 0 on its NOR gate, which means its output stays as 1, and 1, 0 on this NOR gate, which means its output stays at 0. So when our inputs are 0, 0, that means our output Q and Q naught stay at 0, 1. They don't change. Let's flip it over now, and let's say, what if we write a 0 and 1 to S and R respectively? Let's take a look at what that looks like. So if we have a 1 on reset and a 0 on set. Now remember, for the NOR gate, if there's a 1 on any of the inputs, it doesn't matter what the other input is. We're going to have a 0 here, and that 0 comes around to be the input for the S NOR gate, and 0, 0 is equal to 1. So the output for Q and Q naught goes to Q equals 0 and Q naught equals 1. We refer to this as the reset state. Now let's take S and R back to 0, 0. So we have 0 on R and 0 on S. And remember, our outputs are still there, so we have 0 and 1. So 0 and 1, anytime there's a 1, the output is going to be 0. And we have 0, 0, which is our case that gives us 1. So notice that our output now is 0, 1. It's still in the reset. It didn't change. And that's what makes latches really useful. Here we have the exact same input, but the output is whatever it was before. We put it in set and its state and go back to 0, it will stay in the set state. If we put it in reset and go back to 0, it will stay in the reset state. Now there's one more combination here that we haven't looked at, 1, 1, and let's take a look and see what that does. Remember, the 1s dominate the NOR gates in either case, right? So 1 and 1 means that we're gonna have, no matter what, 0 and 0 on the outputs here. So 0 and 0 is an undefined state, right? Set and reset, there's only 2 modes for that. That's the SR latch. Now let's take a look at the not S, not R latch. The not S, not R latch is structured nearly identically to the SR latch. The only difference is it uses NAND gates instead of NOR gates. So it has a NAND gate that goes out to Q and a NAND gate that goes to Q naught. And those outputs also wrap back around, just like they did in the not S, not R latch. Now there's a slight difference in the setup, and that is up here at top where we had reset before, now we'll have S naught. And down here at the bottom where we had set before, now we'll have R naught. Let's take a look at the behavior here. If we have an S, well, S naught and R naught, Q and Q naught, everything here is going to be flipped over. So what we'll see is if we put the not S, not R latch, and we're going to put a 0 and a 1 on not S and R naught. So S is 0, R naught is 1. Now let's remember, what is the input that dominates the NAND gate. In that case, it's the 0. If any input is equal to 0, then F is equal to 1. That means on the not S side, if it's 0, it doesn't matter what the other input is. It's always going to be a 1 on the output here. And then we have 1, 1, which gives us a 0 on Q naught. So this puts it in Q equals 1, Q naught equals 0, which we've already defined as our set state. Now, let's go ahead and let's look at what happens when we add a 1, 1 at the input. Remember, like I said, everything is flipped over from the SR latch. If we put S naught and R naught both equal to 1, and then we have 0 and 1 on the other inputs, when the NAND gate gets 0, remember the output is 1, and 1, 1 gets us 0. So it stays in 1, 0. It remembers the state. That's no change. Now let's flip it over. Let's do S naught equals 1 and R naught equals 0. So S naught's 1, R naught's 0. Now remember, it's the 0 that dominates the NAND gate, so that's going to be a 1 on Q naught, and a 1, 1 on the NAND gate gets us 0. So that's going to be 0, 1. Or the reset state. Let's go ahead and take it back to 1, 1. So we have 1 and 1, and we have a 0 down here, and a 1 at S naught. Remember, the presence of the 0 means it doesn't matter what the other one is. It's going to be a 1. And 1, 1 is still equal to 0. So that means our output stays at 0, 1. And once again, we had no change. Now, just like before, it's possible to have an undefined state. But for S naught, R naught, that undefined happens at 0. Remember, if we have 0, 0, 0 dominates the NAND gate and puts 1s on both the outputs. And so it says Q is 1 and Q naught is 1, which is sort of a violation of even the Boolean algebra there. So that's, again, our undefined, the system catches fire state that we want to try to avoid. So that's the S naught R naught latch, just the inverse of the SR latch. So let's move on and let's take a look at the SCR latch. Now the SCR latch is cool because it adds an extra level of control. So same deal. It's got S on the top. We'll have C down here at the bottom. And we'll have R down here, well, below the C. So, as you might have guessed, the C is for control. And we start by having 2 NAND gates. And the C feeds his input to both NAND gates, and the S and the R go to their respective outputs. Now that circuit feeds into just the S naught R naught latch that we just talked about. So that becomes the S naught, that becomes the R naught. I'll go ahead and draw the circuit in there really quickly. Output Q, output Q naught, inputs that wrap around, and the S naught and the R naught. So let's go ahead and look at that truth table. So if we're going to write it a little bit out of order. We're going to write C, S, R, and we'll see why in just a second. Q, Q naught. So if control is equal to 0, then that puts a 0 on the inputs of both of these NAND gates. And remember, like we've been talking about this whole time, the 0 dominates. And if it's 0, output is equal to 1. So that means that we'll get 1s on the inputs to the not S, not R latch. And as we saw, 1s are the no change output for the not S, not R latch. So when we have C equals 0, it does not matter what S and R are. The result will be no change. What if we add, now let's do C is equal to 1, and S and R are equal to 0. Drives the outputs to 1. And so again, we'll have no change. We'll have that 1, 1 output to our S naught, R naught latch. So we have two instances in which no change can occur. Now, the rest of the time, the circuit behaves basically the same as the not S, not R latch. Let's take a quick look at it and let's work out the rest of these inputs. We'll leave control at 1, and let's try to put it in set. So let's go C equals 1, S equals 1, R equals 0. So we'll have 1, 1, and 0 down at the bottom. So 1, 1 on the NAND gate gets us a 0 input to the not S, not R latch, and 1, 0, or we still have a 0 here, so that's going to be a 1 to the not S, not R latch. So we'll have 0, 1, and if we go back and look at this truth table, 0, 1 is that guy, which sets it in the set state, 1, 0, or set. Now, if we flip it over, we have 1, 0, 1, 0 on S, 1 on C, 1 on R. That gives us 1 and 1, which is a 0, and a 0 and 1, which is 1. And the 1, 0 input to the not S, not R is this guy, which puts us in the reset state. So there's our case, 0, 1, reset. Now there's one last case that we haven't looked at yet, and I bet you can guess what it is, and that's if we have 1, 1, 1. Let's take a look at what that's going to look like. So if we write all 1s to the input, that's 1, 1, which is 0. And that's 1, 1, which is also 0. And as we saw before, that's our 0, 0 input to the not S, not R latch, which puts us in that 0, 0. Oh, excuse me, not 0, 0. Which puts us in that 1, 1 undefined state. So that's the SCR latch, right? It takes the sort of not S, not R latch and lets us add a little bit of control. It also brings us back to a thing that's a little bit more readable. You know, we have set and reset inputs as well as control inputs, as opposed to having not S, not R as inputs, which to me is makes it a little bit counterintuitive. I think the SCR latch is just a little bit more readable of a design. So finally, let's look at the punchline here, which was the D latch. The D latch tries to address that issue of having the undefined state. So the D latch starts with just an input D and the control, so D and C. Now if we go and look at the SCR latch, or really any of our latches, we see that the goal here is to have S and R always be inverted, right? It's when they're equal to the same thing that, you know, nothing happens or bad things happen. So we always want set and reset inputs to be the opposites of each other. So that's what the D latch does. It has an SCR latch that we just looked at, and all it does is it feeds control into control, and it takes D as the S input on the top and inverts it to give us that R input. And we go ahead and quickly draw the SCR sitting in there. It's not too complicated. Q, Q naught. Those guys feeding, the R feeding to the inputs, and the control splitting both ways. And so that's just the SCR latch that we just looked at. And like we said, the only real difference here is we have one input D that we invert to ensure that S and R are always flipped over. So let's go ahead and take a look at those inputs. We'll have C and D, and then our outputs Q and Q naught. So C, as we already saw, if it's 0, it does not matter what D will be. We will have no change. And if C is equal to 1 and D is equal to 0, then it will be in 0, 1, or reset. And if C is equal to 1 and D is equal to 1, then it will be in 1, 0, or the set state. So that's the magic of the D Latch. It takes all of the sort of capability of the SCR Latch. That's why we didn't spend so much time going through the sort of following the bits through the circuit, because all it does is take that input, take the S and R, and just invert to get the R, to make sure that they're always on the flip side of each other. As always, if you have any questions or concerns, please let me know, and I will see you guys in the next lesson. Thank you.